In this video, we're going to take a closer look at mirrors. We're going to look at steps for solving questions about mirrors, show you tools for remembering the steps, and put the whole process in practice with a few examples. There are three standard types of mirrors. Almost any mirror you find will either be flat, curved in, or curved out. A flat mirror is called a plane mirror. A curved in mirror is called concave, and a curved out mirror is called convex. Depending on the type of mirror, you'll approach mirror questions differently. But regardless of the mirror, all light rays will obey the law of reflection. The angle of an incident ray equals the angle of the reflected ray. A great way to begin answering any question about mirrors is to draw a diagram of what's happening. A good diagram will include three rays coming from the object that show where the image is formed. Draw the first ray parallel to the principal axis. When this ray hits a concave spherical mirror, it will reflect back through the focal point. If the mirror is convex, the ray will reflect away, so that tracing it backward, the trace passes through the mirror's focal point. The second ray goes from the object straight toward the focal point. If the mirror is concave, it will pass through the focal point and reflect off the mirror parallel to the principal axis. If the mirror is convex, the second ray travels toward the focal point but reflects off the mirror parallel to the principal axis without ever reaching the focal point. The third and final ray in a ray diagram goes from the object toward the center of curvature of the mirror. For a concave mirror, the ray reaches the center. In a convex mirror, it doesn't. In both cases, the ray reflects off the mirror straight back to the object. The image forms wherever the three rays intersect. So step one in a mirror question is to recognize whether the mirror is plane, convex, or concave. Step two is to draw a diagram. Whenever we have a convex or concave mirror, there are three relationships that often turn out to be helpful. First is sometimes called the mirror equation. This equation connects three things: the mirror's focal length, f, the distance between the object and the mirror, d sub o, and the distance between the image and the mirror, d sub I. If we know 2, the mirror equation lets us solve for the third. The second relationship for curved mirrors has to do with magnification. Magnification depends on a ratio. It says, given that the object has some height, how big is the image in comparison to that? If our image height is twice the object height, the equation says our magnification, m, is 2. If the object and image heights are the same, the magnification, m, is 1. If the magnification is a decimal value, say 1.4, that means the image is 1.4 times bigger than the object. The last relationship has to do with the mirror's focal length and its center of curvature. You might remember that focal length is how far from the mirror parallel rays come together to form an image. For a spherical mirror, the focal length is 1/2 the center of curvature. So whether convex or concave, the focal length equals the mirror's center of curvature divided by 2. When working with mirrors, getting the sign right, positive or negative, is very important, and it's not always easy. This chart lists the variables that normally show up in image questions and what their sign will be. The distance between our object and the mirror is always positive. The object's height is also always positive. The image distance is positive when the image is on the opposite side of the mirror as the object. It's negative when the image and the object are on the same side. The image height is positive when the image is upright and negative when it's upside down. The mirror focal length is positive if the mirror is concave and negative if the mirror is convex. Plane mirrors don't have a focal length. The magnification has the same sign as the image height, positive if the image is upright and negative when it's inverted. Imagine we have a convex mirror reflecting light from a candle that is 65 centimeters away. The center of curvature, or radius of the mirror, is 50 centimeters. We want to figure out how far from the mirror does the image appear. To begin figuring this out, let's follow our 2 steps. First, what kind of mirror do we have? We're told it's convex, which means it curves away from the candle. Second, let's draw a ray diagram of the situation. With those rays drawn in, we see about where the image will form, its magnification, and that it's upright rather than inverted. We've been told 2 numbers. The object distance, d sub o, is 65 centimeters, and the mirror center of curvature, or radius, is 50 centimeters. We want to find the image distance, how far from the mirror the image is formed. We can solve for the focal length, f by using the fact that f is half the distance from the mirror's center to its center of curvature. Since c equals 50 centimeters, f is half of that, 25 centimeters. Remember that for a convex mirror, the focal length f is always negative by convention. So instead of being positive 25 centimeters, our mirror's focal length is negative 25 centimeters. Now we can use the mirror equation to calculate the image distance, d sub I. We need to algebraically rearrange the equation so it says d sub I equals something. First, let's subtract 1 over the object distance from both sides of the equation. Then, we multiply the terms on the left side by d sub O over d sub O and f over f, so that the left side of the equation has a common denominator. We invert both sides of the equation and see that the image distance, d sub I, equals the object distance times the focal length, all divided by the object distance minus focal length. Now let's insert the values of d sub O and f to solve for the image distance, d sub I. The object distance is 65 centimeters and the focal length is negative 25 centimeters. Having the correct signs on the numbers is very important. The fact that f is negative rather than positive, since the mirror is convex, completely changes our answer. We find that the image distance is negative 18 centimeters. That means our image forms 18 centimeters away from the mirror on the opposite side of the object. Now let's look at an example where the mirror is concave instead of convex. Concave mirror questions can be tricky because of all the places the object can be in relation to the mirror. It could be behind the center point of the mirror, or it could be between the center of curvature and the focal point, or it could be between the focal point and the mirror. And in between each zone is another point where the object could be, at the center of curvature or at the focal point. So there are 5 regions where the object might be located, and the image that forms will depend on which one it's in. We saw earlier that there's a way to remember what image will form for an object in any of the 5 regions. Since it's so useful, let's recap that memory device here. When the object is in region 1, the image formed is smaller, inverted, and real, SIR. When the object is at the mirror's center point, region 2, the image is the same size as the object, inverted and real, SSIR. When the object is in region 3, the image that's formed is larger than the object, inverted and real, LIR. When the object is at the mirror's focal point, region 4, no image forms. And when the object is in region 5, between the focal point and the mirror, the image is larger, upright, and virtual, LUV. That covers all concave mirror possibilities. If you can remember SIR, SSIR, LIR, none, and LUV, and what they mean, you will have a huge advantage in answering any sort of concave mirror question. Let's try one out. Imagine you have an object, say a pencil on its end, in front of a concave mirror. The mirror's focal length is 35 centimeters, and the pencil stands 10 centimeters from the mirror. Where is the pencil's image located? As usual, we'll start by identifying what type of mirror we have, and then drawing a diagram of the situation. We're told the mirror is concave. That clues us in that our memory device for concave mirrors will come in handy. Here's what a diagram of the situation would look like. We want to solve for the image distance, d sub I. To do that, we can refer to the mirror equation from earlier. Remember, this equation connects the mirror's focal length, the object distance, and the image distance all together. Like before, we can rearrange the mirror equation to solve for image distance. Now, what is the focal length, f, and the object distance, d sub O? For a concave mirror, the focal length is always positive, so that means f equals positive 35 centimeters. And object distance is always positive, no matter what, so d sub O equals positive 10 centimeters. Now we're set to plug these values into our rearranged equation. The image distance equals 35 centimeters times 10 centimeters divided by 10 minus 35 centimeters, which equals negative 17 centimeters. A negative image distance means the image is on the opposite side of the mirror as the object. That means it's a virtual image. This is consistent with our diagram and with the memory device, which says the image is larger than the object, upright, and virtual, LUV. Let's work through one more concave mirror example, this time with an object in a different region than before. Starting with the same setup as our last example, what if you move the pencil so that its total distance from the mirror is 37 centimeters? Is the image that forms now real or virtual? Upright or inverted? Bigger or smaller? Or the same size as the object? And where is it located? Remember how we begin mirror questions. Press pause on the video and take a couple minutes to figure out what kind of image is formed and where it is formed. Did you find that the image is real, inverted, and larger than the object? Did you get a distance of 650 centimeters from the mirror? If so, great work. If not, let's take a look through the example. We start off realizing our mirror is concave and drawing out a diagram of the scenario. Then, based on the position of the object, we can use our helpful memory device to remember that the image will be LIR, larger than the object, inverted, and real. This checks with our diagram. The image is larger than the object, upside down, and on the same side of the mirror as the object, real. Now, how about image position? We'll again use the mirror equation, modified to solve for image distance d sub I. In this example, focal length is positive since the mirror is concave, and object distance is positive since that's always true. So the image distance equals 35 centimeters times 37 centimeters divided by 37 minus 35 centimeters. After all the calculations and keeping two significant digits, we find our image distance to be positive 650 centimeters. To master mirrors, remember these three things. Number 1, how to draw ray diagrams for objects reflected off of each type of mirror. Number 2, the sign conventions for variables that appear in mirror questions. Number 3, for concave mirrors, the memory device SIR, SSIR, LIR, none, LUV, and what it means. That's a closer look at mirrors. For more physics in motion, go to our homepage where the entire series is available to you.